NASA making a historic announcement today that the Voyager probe has entered interstellar space, that place between the stars. It's now...
Something unthinkable just occurred in the quiet, starless emptiness outside the solar system. Our spaceship, Voyager 1, which had been traveling alone for almost 50 years, flinched out of nowhere. Signals burst from its instruments, which were normally steady and quiet. The plasma disappeared. The magnetism twisted. Rays of the cosmos surged. Then there was quiet. There was no glitch. Everything was examined by NASA engineers. The systems were perfect. Voyager had succeeded. It had responded. How could a spaceship so far away from anything stir? One response surfaced. A hole in the black. Real but unseen and unseen. A rogue black hole moving through space without being noticed. Voyager had been near enough to sense it, too. No warning. No accretion disk. Simply gravity, unadulterated and unprocessed. Flag sensors, Benlight, and released Voyager. The probe survived and recorded it in spite of all odds. It was more than just numbers. It was in the past. The oldest spaceship in human history just narrowly avoided the universe's most dreaded force and survived. At that moment, Voyager 1, which was now 162 astronomical units away from Earth, sensed a dramatic shift. Its devices tracked cosmic rays, magnetic fields, and plasma waves in silence for decades until mission control began receiving inconsistent data from several sensors. The readings were distinct from any noise they had ever encountered, precise, and synced. Had the probe come across something genuine, or was it faulty? Engineers first ruled out hardware issues. Manometers, gyroscopes, and thrusters all worked as they should have. The memory test was successful. The probe itself was the source of the anomaly in the data. As each sensor reported coordinated disturbances, mission control observed. It wasn't arbitrary. It was intentional. Then a terrifying suggestion appeared. Voyager seemed to have sensed the edge of a black hole. In the absence of any observable object, the devices produced indications that correspond to theoretical models of gravitational influence. Just gravity, no accretion disk, no light. It was a historic occasion. Phrases like edge detection, sensor echo, and gravitational event were all over NASA's internal communications. It was more than a fault. As one engineer remarked, Voyager just tapped the darkness and told us the probe, Earth's farthest outpost, might have touched a cosmic unknown. It marked the end of Voyager's lengthy voyage from interstellar pioneer to planetary scout. We must go back to Voyager's beginnings, engineering, and purpose to comprehend why this event was significant and how the ship could even survive such an encounter. This leads us to the second section, Voyager 1. NASA launched Voyager 1 on a mission to investigate Jupiter and Saturn on September 5, 1997. Amazing pictures of Jupiter's storms in Saturn's rings were returned by it. However, the clocks were not stopped there by NASA. In 2012, Voyager continued its journey into interstellar space without cameras. Radioisotope thermoelectric generators, or RTGs, are small nuclear reactors that emit a few dozen watts and power Voyager. Its key instruments are still sending back feeble data from more than 15 billion kilometers distant after almost 50 years. It is a masterpiece of redundancy and engineering from the 1970s. Voyager is now the furthest man-made object, our sole interstellar probe in situ. Although its mechanisms are old, they are made to last. Despite over 2-day round-trip delays, flight controllers continue to guide commands and keep an eye on its condition. Humanity has unparalleled access to the true cosmos beyond our solar system thanks to Voyager's lifetime. Voyager Air was therefore more than just an ancient spacecraft when it recorded an anomaly. It was the only pioneer we had in the dark. We all felt it when Voyager sensed it. Not only numbers were being reported by its sensors, they were covering a momentous occasion. We may now examine what Voyager actually encountered since we have a better understanding of its voyage and the significance of its signals. The skewed magnetic measurements and the abrupt drop in plasma are both indicators of something sinister and imperceptible. And that leads us to the point at which the probe came upon an area that was unlike any other. Later, during a normal data session, the dark one appeared. The irregularity was noticed by mission control. An abrupt increase in magnetic distortion and a decrease in plasma density. The adjustments were made in a timely manner. Voyager picked up a passing or skimming object. Analysts looked at Voyager's trajectory and saw that it fit a suspected dark matter region. Nothing except gravity, no heat signature, no visible light. Out in intergalactic space, a renegade black hole. Almost undetectable, save from the impact it has on its surroundings. The data showed even more remarkable waveforms resembling gravitational lensing. Cosmic rays dispersed, magnetic lines twisted, plasma waves bent. Voyager appeared to have passed near a gravity well without ever noticing it. According to the theory, the probe came into contact with a rogue black hole's gravitational shadow. Only pure, unfiltered gravity is required, no accretion disk. Voyager escaped the trap. It moved close enough to feel the pole before continuing on. We now have actual empirical readings of the impact of a black hole located far from home. The next question seemed obvious given the evidence of a near-miss incident. What precisely is a black hole? We must dissect the formation of black holes and Einstein's theories of the warp structure that can pull on space itself in order to comprehend why Voyager reacted in this manner. Section 4 starts at that point. What exactly is a black hole? We must first comprehend black holes in order to comprehend what Voyager experienced. Despite having a sci-fi sound, these things are genuine and incredibly basic. When a big star falls due to its own gravity, a black hole is created. The core squeezes into a singularity, which is an indefinitely dense point. If the collapse is severe enough, gravity gets so powerful around it that nothing can escape, not even light. It took decades for Einstein's 1916 prediction of black holes to be verified. Astronomers discovered Cygnus X1, a system in which a bright star orbited nothing. In the 1960s, the first credible candidate for a black hole was nothing. We then discovered that black holes are not uncommon. There may be millions in our Milky Way. The event horizon is the term for a black hole's outer border. The point of no return is that, if you cross it, you'll be lost forever. The photon sphere, where light revolves before dropping in or flying out, is located just outside. The singularity, the point where space and time are split apart, comes next. Some black holes rotate as well. We refer to these as Kerr black holes. They produce weird areas where even time twists, known as ergospheres. Therefore, when we claim that Voyager felt a black hole, we mean that it made contact with gravity that was powerful enough to halt time and bend space. It failed to fall in. Although it didn't burn, it had a genuine inio feeling, and the evidence to support that is now available. It's time to examine what the Voyager sensors actually captured now that we know the physics. There was more to the readings than noise. They were coherent, unambiguous, and in line with what we would anticipate in the vicinity of a black hole. The instruments reacted rather than simply surviving, and scientists learned all they needed to know from those reactions. This was an up-close look at something enormous. Throughout the anomaly window, the Voyager sensors respond. Sensors on Voyager illuminated in ways they had never seen before. During my moment, the magnetometer, a device used to measure magnetic fields, exhibited erratic variations. It captured abrupt changes in strength and direction. These were not bugs. They were ordered, rising, falling, as though the spaceship had gone through a magnetic funnel that twisted. The steady buzz of the plasma wave sensor stopped. It was unable to detect anything because of the sudden drop in plasma density, not because it failed. Then, a few minutes later, it roared back as if the probe had gone into and out of a vacuum. It was like stillness with a boundary, according to one engineer. Instruments for cosmic rays also displayed dips and spikes. Rays often strike the probe steadily. However, the count varied during the event, dropping sharply and then rising quickly. This was consistent with gravitational lensing expectations. Particles with high energy bending around a large object. It was a sort of particle shadow that Voyager had traversed. Even the instruments used to gauge Voyager's orientation, the gyroscopes, after a minor displacement, the probe realigned. No malfunction occurred. Something seemed to softly tug on it before releasing it. Nevertheless, every onboard inspection revealed flawless hardware. Voyager had captured the event in breathtaking clarity, and it was true. After obtaining the data, analysts set to work. They sought to track the precise trajectory of the probe and assess the degree of risk it had encountered. Even seasoned experts were taken aback by what they found. It had not been a chance encounter. It was geometric. Voyager had come close to the brink of something enormous, silent, and unseen. Additionally, it had nearly ventured into the unknown, charting the uncharted rift. NASA analysts used the anomaly's data to reconstruct Voyager's trajectory. They discovered something amazing. A renegade black hole had been within tens of thousands of kilometers of the probe. In cosmic terms, that is close enough for the data to bear the imprint of its gravity. However, no one had pulled it in. It had just touched the brink. There was no material spiraling inward, no heat, and no accretion disk. This was not a feeding black hole. It was still functioning, but it was just waiting, sitting there, invisible. It was surrounded by gravitational forces that had dampened plasma, distorted magnetic field lines, and skewed Voyager's trajectory. Density? A whirlwind of communication without any visible validation. The results of magnetic modeling were astounding. Voyager was surrounded by field lines that wrapped and then snapped back. This suggested that the probe may have touched the extreme edge of the black hole vent influence, which is located just outside the photon sphere, the region where light bends but does not descend. This was as close to such a building as any man-made item has ever been. Yet Voyager managed to get away. It recorded, responded, and continued. It is nearly impossible to estimate the likelihood of such a flyby, but it did occur. Not even attempting, a 1977 launched probe has just executed the most audacious space maneuver ever. On a cosmic scale, one astronomer referred to it as unintentional precision. It was more than just an exciting close flyover. It was a treasure trove of science. We obtained direct measurements from a black hole's edge for the first time. Such information has the power to test long-held hypotheses, inspire new ones, and change the nature of physics. Above all, it served as a reminder that even the most secluded locations have secrets and that space isn't empty. Why science cares about it? The unintentional encounter between Voyager and a black hole is more than simply a news story. It represents a significant advancement in space research. Black holes have only been indirectly examined up to this point, either by listening for gravitational waves following large collisions, observing the bending of light, or detecting X-rays from stars being torn apart. However, Voyager provided us with something new. Direct sensor data collected at close range from locations just outside of a black hole's effect. This is significant because it allows researchers to test general relativity in one of the harshest settings imaginable. Time should slow and space should bend around enormous things. According to Einstein's calculations, we may now contrast those forecasts with the probe readings, the live motion recordings of radiation, magnetism, and plasma movement. That is invaluable. Additionally, it provides fresh perspectives on events that occur close to event horizons. Such data has never been available to us. How particles scatter, how gravity alters sensor readings, and how plasma behaves. Each detail aids in the improvement of our models. This can be used to forecast the fate of gas, stars, or even spacecraft that approach too closely. Lastly, it provides us with information about the cosmos itself. Although rogue black holes, those unrelated to galaxies or other observable systems, are thought to exist everywhere, we have never had a trustworthy way to locate them. The data from Voyager provides us with a plan. One NASA physicist stated, "We now know what it looks like to almost hit a black hole." And the game is altered by that. However, every response Voyager provided also brought up new issues. The findings suggested unexpected behaviors. time-like oscillations, odd decay patterns, and even gravitational echoes. Not only was the black hole enormous, it might have been turning, and the implications of that could lead to opportunities we've only imagined. This brings us to Section 8. There were still mysteries, and the information Voyager returned not only met but above expectations. Waves that faded more slowly than expected were among the readings. Gravitational disturbances often subside rapidly. However, Voyager's readings had lengthy tail traces. Physicists were interested in that. Something more intricate, perhaps a revolving black hole, was implied. Black holes that spin are not the same. Known as Kerr black holes, they produce an ergosphere, which is a distorted area surrounding them. Time and space itself begin to whirl at this point. Science fiction, isn't it? Mathematical reality. Furthermore, according to certain hypotheses, the ergosphere may give rise to odd occurrences like frame dragging or even fleeting wormhole openings. Such an incident might have been captured on Voyager. Almost like a moving loop, the readings showed indications of energy redirection. According to some theories, Voyager's gyroscopes and plasma sensors were impacted by a brief ripple in space caused by the black hole's rotation. One expert speculated that we might have briefly witnessed space-time flicker. Then comes the crucial query: would this have been a sign of a wormhole? According to some theoretical models, rotating black holes can momentarily create bridges to other regions of space or possibly time. Though speculative, those theories get new significance from Voyager's unexpected encounter. Perhaps we saw a wormhole nearly open, but we didn't traverse one. Voyager captured something remarkable, whether it was wormholes or simply rotation. Its trip past a black hole was more than just a matter of survival. It was an epiphany. However, the event also changed the legacy of the probe. The planetary expedition turned into something much larger. In Section 9, that is examined the increasingly complex tale of Voyager's role in human history. The legacy of Voyager grows. Voyager had definite objectives when it started in 1997. Take pictures, fly past Jupiter and Saturn, and continue for as long as you can. Nobody could have predicted what it turned out to be. A silent traveler who reinvented adventure and outlived expectations. Perhaps its most astounding contribution to date is its brush with a black hole. Gravitational giant research was never the purpose of the spacecraft's construction. This type of endeavor was not intended for its tools. Nevertheless, it managed to obtain one of the most comprehensive close-up profiles of a black hole ever recorded by science. That fact alone establishes a crucial point. When applied carefully and with vision, even restricted technology can lead to groundbreaking breakthroughs. The tenacity of Voyager further highlights the genius of its initial design. Analog engineering, basic logic, and redundant systems. It's a durability lesson. Voyager serves as a reminder that occasionally durability triumphs in an era of dazzling technology. One engineer commented, "We just got the newest data we've ever seen from the oldest thing we've built." Symbolically, Voyager is no longer merely a scientific instrument or a time capsule. It serves as a reminder that discoveries are made even in the quiet of deep space. This probe touched the fabric of space close to a black hole, launched before smartphones and the internet, and emerged with a message. That goes beyond engineering. That's the past. Now that Voyager's heritage is safe, everyone's attention is on the future. With this data, what are our options? What can we do with this moment? Scientists are getting ready already. New missions are being planned. And what might the upcoming generation of probes discover if Voyager could make it through this? We get to the last part because of that query. What follows? Voyager's encounter with a black hole wasn't solely a triumph. It served as a warning. Researchers are currently searching the data for patterns of uncommon particles, possible gravitational echoes, and ripple fingerprints. These hints could improve our knowledge of interstellar space and aid in the search for further rogue black holes. This marks the start of a new field. One astrophysicist stated, "Gravitational mapping at close range." Engineers are now working on ideas for the next generation of probes. These would have superior sensors and travel farther and faster. Compact LIGO variants designed to suit deep spacecraft are among the designs, as are gravitational wave detectors. Others propose integrating tiny artificial intelligence (AI) systems that are more intelligent, quicker, and completely autonomous than Voyager's, but yet capable of adapting to unforeseen circumstances. Additionally, the incident has rekindled interest in finding renegade black holes around our galaxy. Both telescope-based and probe-based new missions that could create a three-dimensional gravitational map of the Milky Way are being considered. We can detect the undetectable, as Voyager demonstrated. The objective now is to locate more of it. But there's more to it than science. What else might be out there if we can sense black holes without really seeing them? Unusual structures, dark matter, and even life forms that interact with gravity rather than light. Voyager discovered more than just a black hole. A door opened. Conversely, the universe may be far stranger than we previously thought. Something unthinkable just occurred in the quiet, starless emptiness outside the solar system. After nearly 50 years of drifting alone, our furthest spacecraft, Voyager 1, suddenly flinched. Signals burst from its instruments, which were normally steady and quiet. The plasma disappeared. The magnetism twisted. Rays of the cosmos surged. Then there was quiet. There was no glitch. Everything was examined by NASA engineers. The systems were perfect. Voyager had succeeded. It had responded. How could a spaceship so far away from anything stir? One response surfaced. A hole in the black. Not glowing, not visible, but authentic. A rogue black hole moving through space without being noticed. Voyager had been near enough to sense it, too. No warning, no accretion disk, simply gravity, unadulterated and unprocessed. Guide sensors, Benlight, and released Voyager. The probe survived and recorded it in spite of all odds. It was more than just numbers. It was in the past. The oldest spaceship in human history just narrowly avoided encountering the universe's most dreaded force and survived. It was never intended for Voyager 1 to make it to the galaxy's edge, much less listen to anything there. But something suddenly changed after 46 years of wallowing in the dark. Deep in interstellar space, a sudden organized signal was detected that was inconceivable by all scientific standards. It wasn't static. Background noise wasn't it. It was intentional, and it sprang from somewhere we didn't believe anything could communicate. NASA is currently rushing to determine the meaning of this signal and whether we are indeed alone. For the first time, a voice from the emptiness was returned by the silence outside. As it did for more than 10 years, Voyager 1 coasted slowly through the icy emptiness outside the solar system. It had entered real interstellar space since 2012, when it crossed the helopause. Deep black, no more planets, no more solar wind. The spacecraft occasionally returned background noise, faint cosmic ray measurements amid the faint hum of far-off stars. However, until one day everything changed, nothing ever altered. The signal was abrupt. Within the mundane telemetry was a planned, energizing blast that was short, strong, and unlike anything Voyager had ever sent. Several system sensors illuminated at once. Cosmic ray monitor, magnetometer, and plasma wave detector. There was no random static or garbled data in the transmission. It had intervals, tones, and patterns. It appeared to be deliberate. The abnormality was immediately noted by mission control at NASA's Deep Space Network. Something had reached back, but Voyager was not intended to come across anything out there. First, engineers assumed it was a bug. The probe was almost 50 years old. After all, diagnostics, however, revealed no mistakes. Each part reported operating normally. According to one engineer, the probe isn't the cause of the odd behavior. It is the area surrounding it. The atmosphere changed from one of inquiry to one of amazement at that point. Something that had long been thought to be dead had unexpectedly come alive. Voyager 1 had been impacted by an inexplicable force. This was not another telemetry glitch in deep space. It was the first breath of something beyond known physics. One physicist said, The universe had whispered in the great black silence. Our lone messenger had listened in Voyager. Voyager's mission and our understanding of space itself underwent a sea change as a result of the communication. Beyond the helopause, something that had always been thought to be silent and inert suddenly displayed an unidentified intricacy. However, we must first acknowledge the amazing voyage of the spacecraft that captured this anomaly in order to fully comprehend its enormity. A machine that became humanity's furthest ambassador despite never being expected to reach this far. On September 5, 1977, the sole Voyager, Voyager 1, went into orbit. A grand journey of the outer solar system is its mission. It was originally only supposed to survive 5 years, but it visited Jupiter and Saturn, took amazing pictures, and returned tons of data that changed the field of planetary science. However, NASA had no idea how long the spacecraft would last or how far it would travel. Voyager's mission was not simply outlived. It completely fled the solar system. It had entered interstellar space by 2012, the first item created by humans to do so. Voyager 1 is currently over 15 billion miles away from Earth and is traversing a world that is darker and colder than any place that has ever been visited. Every year, its radioactive power source gets weaker. Many of its outdated instruments have been turned off to save electricity. So, it whispers back over the emptiness, sending information from the unknown frontier. There is only a spacecraft the size of a small vehicle carrying a golden record with earthly sounds and human messages. There is no light, no warmth, no breeze, and no planets. It is the only thing exposed to the cosmic abyss. And still it persists. The onboard systems, which were built with technology from the 1970s, are still operational. Its 8-track recorder, its antiquated CPUs that continue to function, and its ability to communicate across time and space. And Voyager sent the odd signal from this silent, eternal frontier. The mystery was only heightened by the isolation. No stars, no storms, no anything in the immediate vicinity. How could something convey a message through that void? What could transport anything thus far out of known space? Or worse, Voyager's location at the time of the surprise pulse is now known. We are aware of the systems it impacted and the sensors that captured it. The data alone did not reveal the most shocking twist, though. Was that part of the motion? Not simply anything was heard by the inquiry. There was a sensation. Furthermore, spin has the power to alter our understanding of the laws of the emptiness and the unseen shock in space, where motion is revered and valuable. Voyager did more than simply record the data when the signal came in. It shifted. There was a slight but noticeable torque detected by the onboard gyroscopes. The spacecraft seemed to be pushed by something. Here's the problem, though. No thrusters had gone off. There was no movement on the reaction wheels. To rotate, there was no internal command. But Voyager had warped physically. It was real, but only for a few milliseconds at most. The telemetry was verified several times by NASA engineers. There was no problem with the gyros. Across redundant systems, the orientation change was reliably recorded. Additionally, they found no evidence of solar wind pressure or micrometeoroid impacts. No influence, no external force, and no anticipated origin. The incident wasn't violent, and one senior flight engineer reportedly mumbled, "We don't have a box to put this in." It was precise, controlled, and most importantly, inexplicable, but it did not harm the probe. After coasting in complete stillness for years, a spaceship abruptly changed its trajectory without explanation. Seeing a ghost push a weather vane was like that. This turn of events, this small shock from nothing, was the catalyst for science to pause and pay attention. Because things don't just move without force in a universe where Newtonian mechanics and conservation rules apply. And it indicates that something else is going on when they do, particularly in areas that ought to be empty. Anything we don't fully comprehend yet. Now that the shock had been verified as genuine, scientists took their usual action. Get rid of the obvious. They went through all of the known sources on the checklist. Far-off explosions, radiation storms, and solar flares. However, none of the typical suspects were there. And the only remaining explanation was much more disturbing after ruling out all other possible causes. Voyager was moved by something out there. And whatever it was left a physical twist but no trace. Movement is sacred in space. Any push, no matter how tiny, endures forever in the absence of resistance and friction. That's why Voyager 1's fate was so unsettling. A little sharp spin was recorded by its equipment. For a second, just a few degrees. However, everything took place without any internal orders. No propulsion, no reaction wheels, no thrusters. It wasn't merely a theory that the spaceship had twisted itself without doing anything to it. Engineers verified that there was a torque. It was picked up by gyroscopes, and the readings matched a momentary rotational force. However, when examining the logs, they discovered that every operational system on Voyager had stayed inactive. According to one systems analyst, we didn't do it, and there shouldn't have been anything. It wasn't aggressive. It did not damage the spaceship. However, the incident made a strong statement. Voyager had been physically touched by something. Was it an impact from dust? The perfect site for a rare interstellar grain? Not likely. No dust surge was present. The surroundings stayed quiet and still. Perhaps a random energy wave, but it would have had to originate from a source that isn't present in the immediate vicinity. There was no known interstellar turbulence at that time. Space itself seems to have shrugged. This twitch, this gesture from the emptiness reverberated with importance in a world beyond human reach, where time is long and gravity is faint. Originally designed to observe rather than respond, Voyager had moved, and not voluntarily. One physicist mumbled, "Something caused it. We also didn't anticipate it." After confirming the movement, NASA looked up into the sky, searching for a rational explanation. However, each possibility just made the riddle more complex. No gamma burst, solar flare, or other intense event in known space could match the effect or time. And as the inquiry went on, even another terrifying insight emerged. It was more than a gesture. The incident had a place, a specific area in the galaxy where an unlikely event had just taken place. Removing the typical suspects. Eliminating the obvious is the first step in solving any mystery. Around the time of Voyager's anomaly, NASA scientists began a thorough forensic sweep of space data. They looked for flares from the sun. Nothing. No supernova remnants. No X-ray emissions. No fast radio bursts. No gamma-ray bursts. Nothing. There had been no sound in the sky. The clocks were in sync. From our telescopes at least, the cosmos had been acting normally. We looked at Voyager Hall's environmental sensors. Readings for radiation were normal. There was no surge in the magnetic field sensors. Detectors of dust particles were silent. Unexpected heating was not detected by thermal instruments. All internal systems were functioning within the expected ranges. Space was empty and Voyager was in good health. NASA was in a unique situation as a result. Even though everything had gone according to plan, an inconceivable thing nonetheless occurred. One mission engineer compared it to seeing footprints form in a sandbox without anyone walking in it. The information was accurate, yet it didn't support any established theory. There were no planets, clouds of debris, or known cosmic objects in the vicinity of Voyager. Since it was traveling through interstellar emptiness, the most remote area we have ever visited, anything that came into contact with Voyager either left no trace or didn't follow the known physical laws. And that's what made the situation so scary. Not that something occurred, but that it was possible for something to occur without cause. However, there was another hidden pattern in the data. A new image started to take shape following weeks of magnetic field mapping and trajectory modeling. Voyager had been more than just a place. It was in a region where known galactic fields should cancel out, which is mathematically odd. A location that was hypothesized but never verified. The mystery gained a new dimension as a result of this twist. What if we were mistaken about the void's neutrality? Charting the impossibility. After weeks of modeling, Scientists were able to pinpoint Voyager 1's exact location during the incident. Then things became more bizarre. The spaceship was traveling through a region in the galactic magnetic field where external forces decreased to almost nil, which physicists have long referred to as a null zone. It can be compared to a calm pond amidst cosmic chaos. There shouldn't be any incidents. Magnetohydrodynamic simulations predict that this area will remain stable. There should be a quiet, peaceful passage when the magnetic fields, cosmic rays, and plasma fluxes cancel each other out. However, Voyager faced disruption rather than tranquilly. It is extremely unlikely that the spaceship will strike such a node by chance and encounter an anomaly at that precise location. It didn't feel so much like a coincidence as a trapdoor. Some scientists started to hypothesize that these blank zones might be more than just passive fields. These might serve as entry points to more profound cosmic interactions, a location where dimensional structures change or where quantum oscillations reach macroscopic proportions. As one astronomer put it, until proven otherwise, we've always assumed space is silent. But what if the exception is silence? The twist in the signal that Voyager received takes on additional significance in this setting. There was more to it than a bump in the road. It was a mapped encounter rather than a chance collision. It was an event connected to a coordinate. Furthermore, we might have to completely rethink how we think about interstellar travel if space can act differently in some places. However, another layer surfaced when researchers worked backward from the anomaly's physical coordinates. Voyager had not simply traveled through an unfamiliar environment. It had detected a frequency, one that carried symmetry, and patterns that defied chance. The tone of the expedition changed dramatically at that point. This was more than just movement. This was not an accident. Someone had spoken to Voyager. Voyager 1, the structured signal, did more than spin. It captured a signal. After examining the data, engineers found a waveform that had never been observed before. Frequencies are interwoven in a layered harmonic pattern that resembles a symphony in space. The noise wasn't random. It was structured, featured nested tones, repeated intervals, and a complicated design that suggested the pulse's purpose. Spectrograms were pored over by scientists. The pattern was not consistent with cosmic microwave background interference, quasars, or pulsars, not magnetic reconnection events, not solar flares. Rather, it was like an energy field, focused, conventional, and coherent. This could be a planned occurrence rather than merely a natural one, according to one astronomer who called it a fingerprint of something we've never cataloged. The physical twist Voyager encountered layers intriguingly with this organized signal. Imagine simultaneously being sung to and nudged. NASA was shocked by the duality. The signature appeared intelligent, but it wasn't human. No known astrophysical source could simultaneously produce a pattern signal and a targeted impulse. When combined, the signature's twist started to read like precise communication rather than verbal exchange. A doorbell on the brink of human reach, a cosmic knock. The probe had received more than a memory after crossing the vacuum. There was an echo, and for a spacecraft that was previously believed to just gather scientific dust, that is the moment that alters everything. This wasn't a quiet emptiness responding with a whisper. It resembled a coded knock on a door more. Alarms also sounded across systems at mission control without making any noise. Not crises, but insight. Possible that something we assumed to be inactive and empty is actually active. There is something out there that can communicate with our craft. This leads us to the response within NASA. The meaning of deep space exploration is being rewritten by stress, silence, and urgency. Within days of the communication, NASA read the code. The tone of an internal NASA message changed. Procedural reports, which were normally quiet, became urgent. Engineers used accurate technical warnings in place of informal check-ins. Unknown interstellar communication. There were flags that were classified. Briefings for mission control were relocated to secure rooms. According to one letter, the probe had caused an extraordinary cosmic encounter known as a level alpha event. Panic over a system breakdown was not the reason. Voyager remained intact. It had life. NASA was alarmed about that. The unknown was always assumed in space missions. Radiation, orbits, but no reaction. This damage could not be repaired. It was communication. We did not establish a cosmic handshake. In an instant, the stakes shifted from an engineering challenge to a scientific breakthrough. Mission planners, physicists, and astronomers meet. They discussed fields, particles, and even the possibility that the universe was deeply improvised and had an intelligent genesis. We are surrounded by presumptions. Discussions changed across fields, with one prominent scientist saying, "This event ensures we can't stay that way." Drafts of papers were made. A few files were even concealed, only for national security observers and directors. Mission control did not take any chances. Each subsystem was examined. Each packet of telemetry is encrypted. There was little data sharing with partners. A threshold had been crossed by Voyager. It was no longer only an interstellar probe. It was a lighthouse. Additionally, NASA was concerned that it might draw attention from observers on Earth and in space. The best discoveries can occasionally be made in secret. However, this was unique. This has nothing to do with sensitive technology or classified planetary photos. This has to do with the unknown and the potential response of the cosmos. That insight raised a question that NASA had never had to deal with previously. When space speaks back to us instead of merely observing us, what should we do? And being ready for that went directly to the next frontier. Redrawing our cosmic charts. The cosmic border is being redefined. Interstellar space was previously thought of as an inert ocean that served as a background for particle detection and celestial navigation. The meeting with Voyager broke that illusion. It was not a passive void. It might communicate, react, and perhaps come into contact with a spacecraft. This implies that every model and mission strategy up to this point needs to be re-examined. Future probes, particularly should we continue with those that target the cloud or exoplanetary missions in particular, may cause reactions that we are unable to foresee at this time if such interactions can take place at vacuum nodes. Trajectories across vacuum zones may be prohibited or at the very least should be avoided, and celestial navigation may necessitate searching for silent field structures. Astrophysicists are organizing to develop new theoretical frameworks on the scientific front. Exotic particles or hidden field dynamics that only become visible at very long distances are now included in theories. Some even propose that macroscale quantum resonance zones, such as strings or nodes, which naturally emerge in cosmic architecture, might exist in interstellar space. The task for engineers has also changed. Develop sensors to identify and decipher these signals, and harden probes not only against radiation but also against unidentified external forces. The experience of Voyager 1 is not unique. There has been a profound change in the way we perceive and investigate the cosmos. No longer is the boundary deserted. It is participatory. And in order to get beyond, we need to develop our ability to hear, react, and move through this new, responsive universe. However, one question remains even after we revise textbooks and update travel plans. What does the universe's intelligence imply from this anomaly? Or was it just quantum oddity in nature? And one ship has been our guide the entire time. Voyager, which leads us to the journey's end and the legacy of a solitary human tip that recently altered our map of the unknown. The legacy of Voyager in the unknown. Voyager 1 started out as a straightforward exploratory experiment and planetary mission. It never anticipated outliving its function. But here, at the boundary of space and time, it conveys messages that alter our perception of the cosmos. Its ultimate function now surpasses that of science. It is an oracle, storyteller, and sentinel. The Voyager signal is difficult to use. It is now listening and returning something, even if we built it to listen. That change necessitates humility. We believed cosmos to be inert. We now know that it can react. Field nodes were assumed to be neutral. We now have a suspicion that they might be interactive strands in space. And we believed that our deed was exploration. To ours, it can now be cosmic. Voyager's experience marks the start of something significant. Our solar-suggested navigation was redesigned, a test for the presence of unknown structure in space. A query: is the emptiness alive, or are we alone? And all of a sudden, that golden record aboard turns into a metaphor. Not only is civilization reaching out, but the universe as a whole is responding as well. The voyage of Voyager 1 is far from finished. Its legacy is only getting started. And one fact is clear: we must acknowledge that the universe already knows us if we wish to understand it. The door is now open. The void has now knocked. Mikri, and our conceptions of solitude, stillness, and nothingness have all shifted. First, Voyager 1 was a silent observer of our solar system. It might now be a sign of something bigger. There is more to a transmission from the void's edge than just data. There is a chance that the cosmos is watching, not just watchable. That area that was previously believed to be empty may actually have purpose or structure. One thing is certain: regardless of the response, our understanding of the universe is altered by something we heard that we are unable to describe. It could be tomorrow or never again before the next signal appears. We're listening now, though, because someone else might be listening as well. The Voyager spacecraft traveled through space in silence for more than 40 years, returning data that most of us don't notice. NASA, however, is now in disbelief over what it found. Voyager didn't simply float in space. At the limit of our solar system, it revealed something startling. For years, everyone disregarded it. An enigmatic border, unexpected shifts in radiation, and fresh inquiries that cast doubt on our preconceived notions about space. What was discovered by Voyager? And why does NASA feel so uneasy? A renowned spaceship that goes above and beyond. Despite overwhelming odds, Voyager 2 has lived for almost 50 years after being launched in 1977 with the original plan that it would only last 5 years, or 10 if the engineers were lucky. It has experienced frigid temperatures, cosmic dust, radiation from the sun, and the vast distances between planets. It still transmits weak signals back to Earth in spite of these unfavorable circumstances, exposing mysteries from the most remote corners of our local cosmic neighborhood. Voyager 2 has now successfully entered interstellar space, following in the footsteps of its twin, Voyager 1. Together with Voyager 1, it is the first pair of man-made objects to cross the line separating the true realm of the galaxy from the Sun's domain. This milestone is supported by quantifiable evidence and is by no means a poetic statement. Its equipment picked up sudden changes in temperature and plasma density as well as spikes in radiation levels, all of which were signs that the spacecraft had crossed from one clearly defined region into another. The changes happened so fast that it seemed as if the spaceship had entered a galactic realm and exited the solar system's bubble through an invisible gate. The results were even more surprising since, in contrast to predictions of a gradual fade-off, these alterations occurred nearly immediately. The scientific community had anticipated a slow decline in solar effect, but instead discovered a distinct boundary that is more akin to moving from one room to another. This demonstrated that the outer edge of the solar system might be more accurate than previous models have ever shown. These sudden data sets also demonstrated that circumstances can get hotter in terms of particle energy, more radiation-laden, and potentially dangerous for any spacecraft that is not constructed with strong shielding just beyond our cosmic doorway. Beyond only verifying the existence of a barrier, Voyager 2 accomplished more. It also highlighted the potential importance of the Sun's own bubble, known as the heliosphere. It used to be commonly believed that this area had no distinct edges and disappeared into the interstellar medium. We now know that after you pass it, the magnetic field changes noticeably and cosmic radiation jumps a lot. This implies that the heliosphere functions as a shield in at least one way. Conditions drastically change the moment you leave that shield, revealing that space is more abundant in cosmic noise and energy than previously thought. The remarkable alignment of the Sun's magnetic field with the interstellar magnetic field beyond was another point of interest for scientists. Numerous long-held assumptions and ideas were contradicted by this. leading to recalculations of the interactions between our solar system and the galaxy at its boundary. The issue is further compounded by the potential for the heliosphere itself to grow or contract in response to solar cycles, which might mean that the border is not even constant over time or between various geographical locations. Interstellar circumstances and rapid, abrupt changes. The most remarkable findings made by Voyager 2 upon crossing this outer border were the abruptness and accuracy of the changes. Evidence indicated a sudden increase in plasma density, indicating that the spacecraft had left the sun-dominated zone. Some describe this as crossing an unseen membrane because of the increasing intensity of the temperature and radiation bursts. It was more like opening a door and finding a completely new temperature on the other side, rather than the slow decline that previous textbooks had depicted. The fact that these values did not increase steadily shocked space scientists. Rather, the changes in data were so rapid that it seemed as though a cosmic boundary had been crossed. The helopor is the scientific word for the boundary of the sun's domain. The preciseness of this limit, which seemed more defined than anticipated, shocked a lot of experts. According to the data, Voyager 2 briefly passed through the solar system before moving into an area that was largely influenced by the larger galaxy. Galactic cosmic rays increased by around 70% in strength outside the heliosphere. The notion that the heliosphere acts as a shield, blocking out a significant amount of high-energy radiation before it reaches the planetary areas where humans live, was supported by that massive rise. Put more simply, there is a functional barrier enclosing the solar system, separating us from the full force of galactic radiation. Voyager 2 was essentially defenseless once it passed through that barrier and came into contact with a high-energy, rapidly moving particle environment. Observing the form of this barrier yielded further insights. Voyager 2's crossing revealed that the heliosphere may not resemble a tidy sphere at all, despite scientists' long-held belief that it is a bubble. Rather, its edges seem pulsing, warped, or uneven. There is evidence that this border expands or contracts as a result of variations in the sun's magnetic field throughout an 11-year cycle. That would help to explain why Voyager 2 met interstellar space at around 121 astronomical units, but Voyager 1 crossed into it at around 119. The discrepancy may suggest a dynamic frontier that is changing rather than being random. Discussions regarding whether the heliosphere is merely one component of a greater cosmic interaction have been sparked by the notion that this zone may not be static but rather living in some way. As Voyager 2 continues to operate, more information will be available to help us better understand how frequently and how much this boundary change occurs. Changes in the orientation of the magnetic fields, fluxes in particle density, and the frequency of temperature spikes have all revealed unexpected features. The idea that things are far less predictable outside of the outer planets is reinforced by every new piece of information. Voyager 2 saw interstellar weather shortly after crossing this threshold. This entails variations in the intensity of cosmic rays as well as fluxes that could be caused by far-off galactic phenomena like supernovas or powerful stellar winds from large stars. However, unlike large telescopes, the spacecraft is not set up to directly view these phenomena. Its equipment can occasionally detect minute changes in particle energy or fluctuations in the magnetic field that could indicate major events occurring in the galaxy. The significance of the heliosphere. The solar wind is the name for the continuous streams of charged particles that the sun emits. A region known as the heliosphere is defined by these outward flows and the magnetic field. Many cosmic rays from other parts of the Milky Way are deflected or dampened by this area, which functions as a sort of cocoon for our solar system. There are actual concerns associated with high-intensity radiation in the galaxy, including as harm to biological tissues or spacecraft electronics. The heliosphere is more than just an astronomical curiosity because of this. It has real-world applications for both space travel and the security of our planet. Researchers have been trying to determine where interstellar circumstances take over and where the solar wind actually ceases for decades. The transition point was formerly thought to be ambiguous. However, The actual Voyager 2 data showed a much sharper border than anticipated, with conditions shifting across a relatively small area. This was significant because it indicated that the solar wind's capacity to deflect or impede incoming cosmic rays was more robust or well-defined than previously thought. Scientists tracked changes in plasma density, charged particle velocity, and magnetic field orientation as Voyager 2 approached that area. According to the findings, the solar wind eventually came to a point where it pressed against or collided with the surrounding medium, creating a border of sorts. The magnetism and particles of the Sun predominate within that border. Beyond it, the environment of the bigger galaxy rules. Our grasp of what it means to state that we left the solar system was improved by this new information. Other hypotheses emerged on the possibility of the heliosphere flattening or stretching in various directions. According to some theories, when the Sun travels through the galaxy, the area behind it may resemble a comet's tail, while the front, which is the direction the Sun is heading, may appear more compressed. The heliosphere is far from symmetrical, according to data from Voyager 1 and Voyager 2. However, it is still unclear to what degree. These and other space missions demonstrate that space weather is not limited to Earth's orbit. The helopor may shift as a result of solar flares, coronal mass ejections, and periodic variations in the Sun's magnetic. Additionally, observations indicated that cosmic occurrences from beyond the solar system may push on this boundary from the opposite direction. It could be further compressed or distorted by small interstellar storms or radiation bursts. Furthermore, the finding that the cosmic ray flux is much larger outside the heliosphere emphasizes the boundary's protective role. It is not that there are hard physical surfaces in the world. Rather, there are ordered flows of fields and particles that result in noticeable variations. Like walking into another environment, the instruments of Voyager 2 demonstrated the stark differences between these habitats. This is crucial for scientists considering long-distance interplanetary travel since, once outside the Sun's protective envelope, spaceships or possibly rudimentary missions that travel so far will have to withstand higher levels of galactic radiation. Startling magnetic field alignment. The near-perfect synchronization of the Sun's magnetic field with the interstellar magnetic field was one of the most surprising findings from Voyager 2's data. A specific angle or mismatch where the two fields meet was predicted by early ideas. It was assumed that there would be some turbulence or a blending region where the solar field and the galaxy's field met. Measurements revealed that they matched up much more easily than expected. This observation suggests that the local interstellar medium immediately outside our heliosphere may be structured in a particular manner. A more smooth interaction might result from the Sun's outflow bending or shaping the galactic field. On the other hand, the area surrounding our solar system may simply be orientated in a way that aligns with the Sun's field. Both scenarios raise additional issues regarding the Milky Way's overall structure and the arrangement of the cosmic environment at these scales. Cosmic ray transit is also affected by this alignment. Many of these high-energy particles are guided by magnetic fields. Complex channels could be created if the fields cross at strange angles. The ease with which cosmic rays enter the solar system may change if they align more directly. Cosmic ray levels quickly increased when Voyager 2 exited the heliosphere, which fascinated observers. The speed at which those particles can stream in may be related to the alignment. Some specialists questioned whether the alignment is constant or if it could alter over the course of the cosmos. Additionally, they noted that although Voyager 1's equipment for plasma were less advanced at the time, it did record some data on the magnetic field during crossing. With more operational plasma equipment, Voyager 2 was able to compare conditions inside and outside the boundary in greater detail. The idea that the boundary behavior defies a straightforward mismatch model was bolstered by this second piece of evidence. In addition, the Sun reverses its magnetic poles during each 11-year solar cycle. This cycle modifies solar wind pressure by increasing or decreasing the intensity of solar activity. It is possible for the heliosphere to spread outward during times of intense activity. In contrast, it contracts during tranquil periods. Which portion of the solar cycle Voyager 2 was in at the time of its crossing may have contributed to the discovery of a tidy field alignment. Even yet, the alignment still calls into question decades' worth of conventional wisdom that were crucial to earlier astrophysical models. Voyager 1 and Voyager 2 crossing differences. Eventually, Voyager 1 and Voyager 2 both made their way into interstellar space. However, they did so in different situations and came to rather different conclusions. At roughly 119 astronomical units from the Sun, Voyager 1 accomplished this milestone by first passing through what is known as the helopause. Upon arriving at the boundary at a distance of about 121 astronomical units, Voyager 2 saw various temperature changes and realized that the crossing was not exactly where it should have been. It also failed to create a carbon copy of the previous data. The fact that Voyager 1's plasma instrument wasn't completely operational when it crossed is one significant difference. Some of the direct measurements were therefore constrained. In contrast, Voyager 2 featured a functional plasma detector, which produced more straightforward data. Voyager 2 results, which showed that the crossing was more like a quick jump than a gradual gradient, provided a clearer understanding of how density changed suddenly. The possibility that the boundary zone is dynamic and changes in size and shape was raised by these unusual readings. Variations in solar wind pressure from year to year may be partially caused by the solar cycle. The geometry of the heliosphere at any given location may also be influenced by local occurrences in the interstellar medium, such as pockets of denser gas or variations in the interstellar magnetic field. The Sun is not stationary, therefore even the direction each spaceship went may play a role. As it passes across the galaxy, it can leave behind a wake or tail. The variation in cosmic ray intensity is another interesting aspect. After leaving the heliosphere, both vehicles experienced an increase, but there were minor differences in time and amplitude. This implies that a variety of factors, including solar flares and galactic environment disruptions, may be at play. The specific numbers demonstrated the complexity of the actual boundary interactions, even though the broad idea of increased cosmic ray flux outside the heliosphere was consistent for both probes. Furthermore, the boundary is not a simple shell, as evidenced by the fact that Voyager 1 and Voyager 2 observed radiation discrepancies that were less than $2 apart. Imagine it as a membrane that can be more compressed in certain places and protrude out in others. These reductions and expansions are not merely hypothetical. Every time either probe passes a particular place, they appear in the data. Both missions' ongoing research offers a real-time laboratory for studying the passage of star wind into the larger cosmos. Proof of a border in motion. Voyager 2 data demonstrates how solar winds and cosmic forces interact intricately to generate a shifting frontier. Conventional representations depicted the heliosphere as a fixed barrier, but each Voyager probe passage highlighted the possibility that it could change or oscillate. An excellent analogy is to think of a cell membrane, which has the ability to bend or interact in tiny ways with its environment. This area receives energy from the Sun's magnetic cycle, which causes it to periodically grow or contract. The wind gets stronger and pushes outward when solar activity increases. The border shifts inward as a result of increased interstellar force penetration during activity decreases, because of the increased magnetic pressure close to the boundary during heightened solar wind. Cosmic rays may be able to go a little farther. However, cosmic rays can establish themselves and move closer to the inner solar system when the wind is weaker. Additionally, this pulse-like activity may produce areas where the boundary may eventually be ripped or disrupted, creating confined spaces where interstellar particles may seep in or mix with solar particles. According to some stories, scientists have compared the outer area of the heliosphere like a living cell that breathes in time with the cycles of the Sun. The Sun experiences flares, plasma ejections, and polarity changes over an 11-year span. Each of them affects the heliosphere's extent and form. Consistent broadcasts from Voyager 2 aid in monitoring these changes by demonstrating how abrupt increases in the number of charged particles or changes in the density of plasma may occur simultaneously with or after solar flares by a specific amount of time. The impact of outside influences is also noteworthy. The Milky Way has areas of different densities, and the solar system moves across it at a significant speed. Others have powerful magnetic fields from former supernova remnants, while others have more dust or gas. It is possible that the heliosphere will adjust if we drift into or out of any such zone. Even while they are unable to monitor every tiny cosmic event, scientists can observe how outside forces can alter the boundary values that Voyager 2 recorded. The speed at which these shifts took place was one aspect that caused considerable concern. We may anticipate a progressive ramp in the data if the boundary moved gradually, yet there were sudden changes. This sparked conjecture that the border might contain more slender areas arranged in layers or rings. The vessel would experience brief variations in temperature or cosmic ray count while traversing these rings. The idea that space is a patchwork of microenvironments created by magnetic interactions rather than a smooth gradient is supported by such abrupt jumps. Voyager 2 helped scientists better understand the 2019 blackout, odd signals, and the architecture of deep space by giving them concrete evidence to support these beliefs. The incredible voyage of Voyager 2 has not been without setbacks. The inquiry went through a temporary blackout in 2019. When instruments went offline, engineers on Earth observed an unexpected shutdown. After that, the spacecraft appeared to reboot itself and returned a few hours later without any help from humans. Officials referred to it as a bug and suggested that it might be caused by software or old technology. However, several observers questioned if the event might have been caused by impacts from the nearby interstellar environment. A few anomalies with strange spikes in electromagnetic readings have also been documented. These surges are frequently linked to far-off cosmic occurrences like gamma or supernova explosions, whose consequences take time to manifest. Even yet, a few minor variations did not precisely correspond with recorded occurrences. There is a persistent interest in determining whether the environment outside the heliosphere might include aspects that we are yet unable to completely detect, even though such oddities are typically attributed to hardware noise or random electronic problems. Voyager 2 is closely monitored by engineers at NASA's Jet Propulsion Laboratory, yet they are limited in their actions. There is a considerable delay because commands travel great distances at the speed of light. The autonomous recovery procedure of the craft may have to deal with a subsystem failure before teams on Earth can even respond. Voyager 2 was able to survive the blackout period thanks to its independence. Additionally, there are rumors, documented irregularities, or data trends that don't exactly match up with recognized cosmic occurrences. It is difficult to distinguish between an internal sensor malfunction and a real external signal because the probe is operating on older systems and is well beyond any direct maintenance. However, these signals stoke conjecture about what could be hiding in interstellar space's lonely regions. Are there any undiscovered phenomena? Or is it just an indication of aged hardware? Astrophysicists can still benefit from Voyager 2's ongoing signals regarding plasma waves and the magnetic environment surrounding its trajectory. Every new piece of information, whether expected or not, is thoroughly examined. Some changes manifest as little increases in cosmic rays or changes in the local magnetic field, coinciding with solar events that eventually travel that far in space. The mystery could be further compounded by others that match with no known solar trigger. Is a monitored frontier possible? Some have put up the intriguing idea that the heliosphere boundary may be monitored more broadly in addition to serving as a protective barrier. Voyager 2 data suggested the abruptness and precision of the change. The vessel appeared to cause an instantaneous reaction in the environment rather than a gentle, progressive drift. The notion that the solar barrier might serve as a checkpoint has primarily been discussed in speculative circles. Note that this is merely an interesting idea and is not supported by mainstream science. Such rumors were nevertheless fueled by the spectacle of leaving the solar bubble and entering interstellar space. where nearly instantaneous changes in radiation, plasma properties, and the steady alignment of the magnetic field were observed. Critics suggest a more straightforward explanation. Cosmic fields are dynamic by nature, and whenever a star's outflow encounters the interstellar medium, a sharp boundary may naturally form. At some distances, there may be abrupt transitions between the magnetic field lines of a star and the galactic field lines, forming a clean pattern. There has also been discussion on how it may be viewed as audacious to transmit the golden record along with explicit directions on how to locate Earth. It might be dangerous to broadcast our location if the cosmic environment at our boundary were, in theory, more conscious or structured than we think. But any reference to real watches out there is merely conjecture and not a genuine scientific finding. According to NASA's official position, the limit's sharp character results from known physics rather than from gatekeepers or observers. Voyager 2 reported spikes in the world of pure data, which some people believe to be the passing of a sensor threshold. For a well-defined border, the abrupt increase in galactic cosmic rays and the corresponding change in the magnetic field are recognized occurrences. It is debatable whether that barrier is monitored or merely differentiated. The question is whether the border can change in real time and how consistent it is throughout the solar system. Instead of seeing it as a purposeful perimeter, some astrophysicists view it as an extremely sensitive interface that responds to the interaction of forces. The question of whether the sudden shifts point to an unidentified interstellar layer that could concentrate radiation is the second angle. If this is the case, Voyager 2 simply passed through an area where cosmic radiation intensifies because of natural field lines, without setting off any further earthly alarms. Even if these explanations are less dramatic, they are nevertheless consistent with data-based physics, even if the craft's glitch or anomaly was an unconnected event. In any case, both mainstream scientists and others who like to consider more creative perspectives, adaptive borders, and different distances continue to focus on the boundary's stark topography. The fact that Voyager 1 and Voyager 2 crossed this boundary at somewhat different distances and documented slightly different conditions was one of the major surprises. The specifics, such as the suddenness of the plasma shift or the size of cosmic ray bursts, differ, even though they both verified a wall-like transition. The borderline is not the same in all directions. According to the researchers' findings, every viewpoint could produce a different interpretation. Additionally, we have compelling evidence that the heliosphere is not exactly spherical, with parts that extend farther from the Sun and parts that stay closer. Many now liken it to a teardrop or a comet-like shape. Over the course of the Sun's 11-year cycle, this form changes. The barrier can be forced outward when solar winds are strong. The outside region recedes when the Sun is calmer. These edges can be further distorted by interactions with dust streams, gas concentrations, local interstellar circumstances, and other star influences. Furthermore, Voyager 2's measurement of the difference in plasma density provided information on the potential compression or expansion strength of the nearby region. Cosmic rays find it increasingly harder to penetrate farther into the solar system if the barrier region has a higher plasma pressure. Based on external and solar-driven factors, observations reveal that the border can stretch, allowing slightly more or less cosmic rays to enter. Consequently, the concept of an adaptable boundary is not merely theoretical. There is consistent data to back it. We do not perceive a static limit in that regard. Rather, the boundary functions as an interface that reacts to influences from both inside the Sun and outside the rest of the galaxy. Both the region it passed through and the level of solar activity at the time of crossing were reflected in the circumstances that Voyager 2 recorded differently than Voyager 1. To get a three-dimensional picture of how the heliosphere might change along its edge, NASA requested 2 spacecraft moving in different directions. According to some scientists, even a single cosmic event can trigger solar wind pulses that radiate outward for months or years before arriving at the helopor. Such pulses may cause a transient shift in the boundary or produce noise that alters the temperature or density when they impact with it. The probe may detect that disruption if it is out there at the correct time. It may be able to pick up waves that move through interstellar space if it has already crossed the border. The boundary may eventually move once more with the Sun's subsequent cycle. When Voyager 2 returned the last confirmations of its journey into interstellar space, it revealed a well-organized but unexpected environment. It compelled fundamental beliefs about our cosmic situation to be reconsidered. Many people have historically thought of space as silent emptiness. The idea now is that the solar system itself resembles an enclosed bubble surrounded by a zone of magnetic and plasma-based structure rather than a solid barrier. There is evidence that space is stratified, with the solar bubble at the boundary and the galactic environment beyond, which has a different field alignment and higher cosmic radiation. These revelations highlight the fact that we haven't just been aimlessly floating through space. It's possible that we were shielded by the Sun's protective shell, enjoying less cosmic radiation inside, and we only became aware of how significant that shield was when we looked at the difference outside. According to data from Voyager 2, crossing that line exposes vessels to a zone that is more turbulent and intense. The abrupt shift in results suggested a more acute physical barrier than previously thought. While the galaxy's magnetism forms the exterior, our star's magnetism has a significant effect on the interior. The sudden temperature increase, the almost perfect field alignment, and the powerful cosmic rays all pointed to a more dramatic scenario than previous theories had suggested. Because of Voyager 2's ongoing work, we also know that the border can move periodically or from one location to another. It may even react to local cosmic processes or more general occurrences like solar flares. Beyond the realm of actual science, the idea that there is a line that may be crossed so forcefully arouses interest and apprehension. For example, if it is ever located, the golden record it contains raises the possibility of contact. Some fear unknown dangers, while others applaud the audacity of broadcasting Earth's presence. However, that record stays exactly as it is, maybe for millions of years, drifting to an unknown place. That small disk will remain in the cosmic dark even after the craft's power is cut out by 2025 or so. By defining the distinction between the interior and exterior environments, those who previously thought that the heliosphere tapered off gradually now need to imagine organized layers around the very boundaries of our Sun's sphere of influence. Additionally, Voyager 2 verified that cosmic rays are much more powerful outside of our bubble. It proved that the boundary between the heliosphere and another cosmic region is marked by actual, quantifiable changes. The way scientists perceive interstellar conditions, magnetic lines, and planetary system limits in general, as well as how mission planners see deep space research, is influenced by this new viewpoint. Thanks for watching another episode. Please like and subscribe for similar content.